Okay, we'll see how well this works for a while. So what we're going to do in terms of assignments in the math part is I've worked with the TA a little bit. He gave me some of his ideas. I like where he's going. There'll be some problems of the type that we're looking at right now. Because this book is out of print, and I don't know, can anyone, well, let's do this the easy way. How many of you have a copy of Sham's edition 1? I don't see very many hands. Okay, so it's still less than 10 people. Okay, well, I'll see about maybe providing an image of the problem I want solved. Is it just not available, or are you not enthusiastic about purchasing it? Sorry? It has to be edition 1 because it corresponds to the problem assignments here. Yeah, it's on Amazon. It's either in the mail. Is there a, well, I'm not going to ask that question. Is there a non-paper version of it available? So tonight what we'll cover is the rules of algebra, the concepts of functions, polynomials, logarithmic functions, trigonometric functions. Additionally, we'll do some simple calculus, some series, convergence of series, Taylor series, partial differentiation, matrix algebra, Leibniz rule. Leibniz rule comes up very seldom in petroleum engineering problems, but it's useful for pseudopressure. That's where we'll see it. Complex numbers and complex arithmetic, I admit, I don't know anywhere where this comes up. Maybe, uh, anybody know in petroleum engineering where complex numbers appear? Phase behavior, I know we had a cubic root solution that we had to take had to use complex arithmetic to calculate the roots. Then be familiar with calculus, limits, derivatives, integrals, etc. This is going to be the easy part, and I can assure you that most of you are going to be bored to tears. If I were sitting where you were, I would be rapt with attention because I spent much of my career at your age trying to relearn all the things I never learned. By the way, the pizza is getting cold in the back. I guess I should like help yourself. So do it in 2 minutes or less. I'll talk while you're moving, and just keep going. I'll talk. You can, if the room was on fire, you wouldn't move any slower. So again, the book that you'll need, as I pointed out a moment ago, David, this is the first edition. This is a 1971 text. That's the whole point, is it's edition 2. It has to be first edition. Otherwise, the problems are different. It has to say copyright 71. It has to be that ISBN number, and so on. I know I should just assign a textbook for this and, evolve, but that's not my thing. Okay. So these are some of the problems that I was advising you to work. There's an old joke from the 1970s, or an old comment from the 1970s. You may see these again. So I suspect some of this will come from some of the problems that you'll see may come from here. There are some problems referenced to the calculus text as well as the advanced math for engineers and scientists. One of the things I like about the Advanced Math for Engineers and Scientists book is it has good worked out solutions. Does everybody believe everything they read? Do you believe that every book has perfect answers? Yeah, good answer. So there were a couple of problems that I assigned from this text that had juxtaposed numbers, like in the numerator and the denominator of some partial fractions things, or maybe there was even an error that crept in. So just be aware that although you're to reproduce all steps and so on. One of my favorite problems to assign, which you will hate, is the so-called method of Frobenius. Have you guys ever used that before? No? The method of Frobenius is a method for deriving a generalized solution to an ordinary differential equation. It uses a power series, and it turns out that, if you have at least some algebraic mind, you should be able to derive a solution, say for Bessel functions, in terms of the method of Frobenius. It is, and I quote, not fun, but it is a useful exercise. Like a lot of things we'll talk about tonight, it's more historical than it is current. But remember, the reason we're talking about these things is when computers first came out, the only operations you had were addition, subtraction, multiplication, division, and logic. You did not have Excel. You did not have Mathematica. You did not have MATLAB. You did not even have the ability to calculate a logarithm. There has to be an equation put in somewhere to calculate the logarithm. I know I've discussed this with you before, but this is important. This is why we're covering some of this material on these kinds of calculations. Also, when we start talking about integration and differentiation, those may be useful for certain kinds of functions. David, for example, your problem is non-integrable. So, well, it actually does have an integral, but there's another version of an equation that is non-integrable. And what do you do when you have something that's non-integrable? Well, you cheat, and you either break it into pieces until you get something that is integrable, or you have to do it numerically, which is a possibility either way. Okay, so let's start first by looking at definition of derivatives, and agreed this is poor quality, needs to be redone, slap my wrist, whatever you want to do. But the definition of the derivative is the limit as the difference divided by the partition. That partition goes to 0. And what that's telling you graphically is if you have this distance across which you're estimating a chord slope, the more you collapse that distance until it's an infinitesimally small distance, the more accurately you represent the tangent. Again, this is more of a refresher for those of you who may have forgotten all this, but sort of finite difference calculus is important. It's going to be used for a lot of things in petroleum engineering, particularly for numerical simulation, obviously. So the real question about this is a continuous function. What about a data function? Can you use a formulation like this for a function made up of data points? What's going to happen if you do? And this is where all of your theory and all of your smartness and everything else that you have as young people is going to break down. All of this is for analytic functions. What happens when you start dealing with discrete functions? Anybody? I had it yet again this week. Well, it was Friday, pardon me. But someone sent me a note and they were trying to differentiate data, real data, and they were using Excel and they were getting a cloud. Why? Because real data has little, bits of noise in it, and when you try to apply a finite difference formula, what's going to happen? Boom. It's going to amplify and magnify that noise. And as our good friend Mr. Jose, who runs Kappa Engineering, says, the derivative of a cloud is a bigger cloud. So how would you get rid of this? How would you make something like this work for you? Well, you could get very cunning and you could use a spline, or you could use some sort of a moving curve fit. All of these things have been done. You could also cheat and try to reformulate the problem in terms of a different kind of calculus. I've tried that, say take the Laplace transform of the data and try something like that. But of course, the Laplace transform helps you in one sense, but then when you come out of the Laplace domain, you amplify the error again. So just sort of planting a seed that we need to think about non-analytic functions. They're going to have some problems. So the rules for differentiation, the first one is a chain rule. dy dx is equal dy du, du dx. Everybody knows this. And you can go du dz, dz du, blah, 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 all the way down to as many variables as you need. The product rule is the derivative with respect to x of two functions uv is equal to u times the derivative of v with respect to x plus v with derivative of u with respect to x. Somebody impress me. How do we derive the method of integration by parts? We start with the product rule. Okay. Sorry? And then you just integrate. That's correct. That is the product rule. Okay. And then the quotient rule is the same as a product rule, except you're dealing with u over v, so you have to carry through those pieces and parts. You end up with something that looks a bit different. It's 1 over v du dx minus u over v squared dv dx. And again, the quotient rule, product rule, you'll keep those in mind. The power rule is the derivative of, with respect to x, of some variable u raised to the power p, where p can be a real number, is p multiplied by u raised to the power p minus 1, and then du dx. I know this is trivial, but we got to remember that everybody in here is getting a refresher. Next is the fundamental theorem of calculus, and this is really the definition of integration. I'm going to go ahead and jump to this part where we'll define integration as the area under the curve. Typically, integration is defined with rectangles. As you can see, rectangle A1 plus rectangle A2 plus rectangle A3 plus rectangle A4. The smaller we go with the partition, the better we approximate the area under the curve. So obviously, at some point, that partition goes to near 0. This would be the equivalent of just adding up rates or something like that, or well, if they're on an evenly spaced basis, you could add them up. If they're not, you'd have to multiply the rate times the duration and then add those up. What would be better than using a strip here? Well, it'd be to use a trapezoid. And what would be better than a trapezoid? To use something with an arc. So guess what the name of the method with the trapezoid is? The trapezoidal rule. What's the name of the method with an arc? Simpson's rule. Okay, and we can keep going on and on with more advanced terms. Obviously, it depends on the function you're integrating and what your goal is. Again, to go back to functions which are non-integrable, you may want to use something that's highly accurate, Romberg integration or Gaussian quadrature. There may be a reason for using Simpson's rule or the trapezoidal rule, but you may also want to go to something more elegant or more rigorous. The next slide is talking about the rules of integration. And basically we have, when we start looking at the reflection relationship, this will come in, this is just the definition here, but when we come in to looking at the integral from a to b of f of x, it's equal to the negative of the integral of b to a, and that's for b greater than a. This is so-called reflection relation. We will use this later on in the course when we talk about fractured wells. It's useful for us to switch our orientation of one of the two integrals. We would like the integrals to be from 0 to x, for example, and one of them is from x to 0, so we'll flip it that way. There's a commutative rule that basically says that if you're integrating a function f of x plus or minus g of x, then you simply add or subtract the resulting integral, as you can see by the commutative rule. Then, of course, there's multiplication by a constant, which I think is pretty obvious. And then we can start breaking integrals up. We can have the integral from a to b of f of x, which is equal to the integral from a to c of f of x plus the integral from b to c, from c to b, my apologies, of f of x. And then, of course, we can switch around and make c be our origin, so we end up with c to b and then c to a, but of course we have to have a negative sign. And again, I want to emphasize that we will use this for our fractured well solutions late in the course. This is the kind of thing that is very helpful. Also, sometimes, it's good to have a sort of a history lesson, and late in the course you'll find that Mr. Jose, Mr. Ramey, and Mr. Horn at Stanford, they derived a very elegant solution to the case of a fractured well with naturally fractured reservoir aspects to it, but they ended up with an integrand that was not integrable in the form they wanted. So what they did was they integrated it numerically. And you're going to see a few problems in this course where somebody else comes along, let's say Ruben, and he looks at it and he says, that's just a variable of transformation. I'll define a new variable, redefine the integrand, out pops a direct solution. So sometimes that happens. It can be very tedious because you may not know what the outcome looks like. But in the case of the solution for fractured wells, like I mentioned, Ozcan and Raghavan, they just sort of said, oh, you missed it here, flip this, substitute that. And there was a lot of algebra involved, but they basically ended up with a direct solution rather than a numeric solution. So, something like that may be valuable for your own research. Next slide talks about integration by parts. We've already mentioned all you have to do is multiply through by dx and then integrate. So we take the product rule in its previous form, multiply through by dx, and then integrate, and this gives us our integration by parts rule. So if you ever forget how to do integration by parts, just remember the product rule. Okay, so I'm going to treat you like you're young and easily impressionable and so forth. Why would you use integration by parts? What's the goal? Everybody in here knows the answer. Somebody say it. To take something complicated and make it easier. But, and this is real life, if you don't choose the integration by parts components correctly, you end up with something worse. And that's sort of like, I started to say marriage, but let's just say relationships. That's terrible. I'm sure it's being recorded and somebody's going to send the video to my wife, but that's not what I meant. Okay. But if you do not choose, or if you cannot reduce the complexity of the integral using these substitutions, then it's probably not reducible. So dv, which is the part that you're going to integrate, it needs to be readily integrable. If it's not, stop. You've probably got a problem. And then the integral of v du should not be more complicated than the original integral u dv, or you got a problem. It's not going to reduce your work. There's some, this is mostly for book problems and that sort of thing, but it does arise. Again, I hate to keep coming back to fractured wells. The reason that we keep talking about fractured wells is that you're going to integrate a line into a plane. So everything that we had before that was pretty easy. It was just we were dealing with a line source solution, maybe radial coordinates or that sort of thing. But once we start integrating something again, then you end up with something like this where it's going to have some sort of a reduction or some sort of a clarification, or you could end up with something really ugly. And when we start the derivation of the fractured well stuff, you're going to see what I'm talking about. There's some really ugly integrals, but they do eventually come down to earth, so to speak. Looking at integration, again, if we have an increasing function, then what happens, class, if you use rectangles? If we have an increasing function, then you'll always underestimate the integral. If we have a decreasing function, you'll always overestimate the integral. And, essentially, like I said, all we're going to do is add up the areas A1, A2, A3, A4. Once we add the partition that's a triangle up here, that would be the trapezoidal rule, and so on. Just out of curiosity, how would you program, well, if I gave you a table of data, would you assume that, how would you start? Let's just do a real quick class problem. If I gave you 10 numbers, and over here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and over here is some other numbers, and I told you to integrate it, what would your first tactic be? Just to calculate the difference between each of the arguments, which is 1, and then to multiply it by the height? Is that what you would do, and add it up? Okay. Is there another, what about using the trapezoidal rule? Is it overkill? Do you think the trapezoidal rule is necessary? How would you know? What would your first instinct be? Plot it. Yeah, very good. Okay. And see what it looks like. And of course, Excel is horrible for this because it's either going to connect it with lines or it's got this smooth curve function. Do not use the smooth curve function. Sooner or later, you're going to get into trouble with that. But the smooth curve is some sort of a spline that's going to point. That's why it's got all the wiggles in it. I would encourage you to plot your data first and make a decision about whether or not you want to deploy the trapezoidal rule. Again, I'm talking about for data. But this would be a first pass, and again, I want you to remember that if you have an increasing function using the rectangular method, you'll be too low. Using the if you have a decreasing function, you'll be too high. Nobody said anything about the first partition. Comments? Well, from 0 to A, what's going to happen here and what's going to happen here? Sorry? Okay, so you're saying that you would come in with a trapezoid or with a, with a triangle right off the bat here, and then what would you do over here? Well, you would, 0, A, and then F1 of X, define that with a triangle. Yeah, but I'm saying, what are you going to do otherwise? You're going to leave it open? I mean, this is definitely going to hurt your integration. Now, nice function that this is, it starts from 0, so everything's cool. What if this function goes straight up? Can you think of a function that goes straight up? How about 1 over x? Yeah. So right off the bat, we have an interesting characteristic behavior there. All right, we'll come back and talk about that later on, but I want to plant the seed. Okay, so now we define the trapezoidal rule, and as we discussed before, we're simply going to add a triangle. So we have a rectangle, now plus a triangle, rectangle plus a triangle, rectangle plus a triangle, and so on. You can see this little sliver right here is actually a bit of an arc. And again, we're making the assumption that it's quadratic, which would allow you to define it with Simpson's rule. So the area of the rectangle is just the delta x, or the h, multiplied by fxi, which would be here. And then the triangle is 1/2, again, the base, which is the h across here. And then we're going to separate the distance here to here, and that allows us to define the triangle in that fashion. We come up with a formula that when we're done, the area of the trapezoid is the base divided by 2 multiplied by these two plus each other. So that may be an interesting algebraic artifact, but it ends up being this one plus that one. So it's sort of a halving formula if you want to think about it that way. And then, you can sum these together and that gives you the trapezoidal rule. What does it not give you? What does this graphical derivation of the trapezoidal rule not give you? It does not give you the error term. Okay. And how would we derive an error term? We would have to go in with finite difference calculus and derive the trapezoidal rule with some sort of a functional approximation, and then we can define our error term based on the limit of that functional approximation. That is in the Hornbeck text, and I probably won't assign it. I have in the past, but it's a nice derivation to do that and the Simpson's rule, but let's see how I feel. Now let's talk about the definition of exponential and logarithmic functions. First will be exponential, and I used to give this as an assignment, and I know the rule is you should never give anything to the students that you can't do yourself, but this is a knuckle buster. If anybody knows of a trivial solution for this, then tell me, but this one is pretty tough. And then, of course, we can derive a Taylor series formulation for the exponential, and we'll do that in later lectures. And that just becomes a Taylor series formulation like this, or if you condense it down into an infinite series, it looks like that. This is the interesting one to me, is because this is actually the definition of the exponential function. Really kind of clever. Some of the special values are exp of 0 is equal to 1, exp of 1 is equal to e, which is 2.71828 ... Exponential of infinity is infinity. Exponential of minus infinity is 0. Had an exercise today with one of my students who was trying to find out why his computer code was failing at large times. Can you see where a computer code might start to fail at large times off of this particular discussion? Where would it be? At large negative arguments? What's supposed to happen? It's supposed to go to 0. But computers don't really understand that. In the old days, you would get a printout that would say on unit error for 0 divide, or value unknown or something like that when you exceed machine precision with your negative large argument. And the same thing is going to happen with Bessel functions. Every computer program out there, whether it's Mathematica, MATLAB, C++, Pascal, Python, whatever, is going to have some machine limit on this. And it all depends on how those arguments behave as to whether they're going to converge or not, just as a comment. The operators are the derivative of the exponential is the exponential. Of course, it's multiplied by the exponent. The integral of the exponential is the exponential, of course, divided by the exponent. When you have two functions, x and y, which are exponentiated, it's exp of x to the y, or exp of y to the x. And then when you have two exponentials that are multiplied together, it becomes exp of x plus y. Now, I'm sure you know this, and we're about to change to the discussion of the logarithm, but the exponential is our primary sort of variable when we're looking at things. We don't very often change to a log base 10 for use with exponentials. There may be some applications, but I haven't seen them in 30 or 40 years where you would see anti-log 10, which would be the base raised. It would be raising something to the base of 10 to a power. We usually work in exponentials. When we start talking about logarithms, 99.9999999% of the time, we're talking about ln, the natural logarithm, except when we start plotting things on paper. Then what do we use? We use the log base 10. Why do we use the log base 10, class? We don't have log base e paper, do we? E to the 0, e to the 1, e to the 2. Why do we use 10? What's the bad luck number in Chinese? 4? Yeah. How come we don't use base 4? What if there's another planet where people have 8 fingers, and they're used to working in 8 and maybe 8 toes? Could they then use log base 8? Are we just accustomed to 10? Yeah, that's what it is. So when you go to sleep tonight, think about using log base 7, or think about using, log base pi or whatever. But we only have 2 that we're really going to use. What are they? E, which is going to be everything in this class, and then 10, which whenever you go to well testing or production data analysis or anything where you're actually going to plot something on a logarithmic scale, it's going to be a log base 10. And we'll talk in a moment about a mnemonic for remembering that. So the definition of the logarithm is over here. And you'll notice in some of the older assignments, if you could find them, that if I ask people to calculate the integral of, say, x1 to x2 for this 1 over x argument, if they didn't show me that that was log of x1 minus log of x2 or whatever it might be, with the calculus, I took off full credit, because I wanted them to understand that it's not just a simple operation. You can't just say that the logarithm evaluated from x1 to x2 is simply log of x2 over x1. You have to work out all the algebra for that, and we'll talk about that. That's actually down here in this argument, where the log of x over y is equal to the log of x minus the log of y. That's the rule. You would be creating an integral that you'd be saying, okay, the log of x minus log of y is just simply the log of x over y. And that's where I was talking about up here. But you need to memorize this if you can. What's the implication of this definition, class? Something obvious. Anytime x is less than 1, ln of x is going to be negative, right? I know, trivial, but I thought I'd bring that out. There's a couple of series expansions for the logarithm. They're not very good, but there they are. And then there's some special values over here, just like we had for the exponential. Keep those in mind, however you may want to use them. The nice thing about the logarithm is its derivative is 1 over x. You can keep differentiating it, and you just get higher and higher negative powers of x. That might be of value to you in a derivation. The logarithm of xy is equal to the logarithm of x plus the logarithm of y, just like we mentioned a moment ago. The logarithm of x divided by y is the logarithm of x minus the logarithm of y. And then the logarithm of x to the a is equal to a logarithm x. And I mentioned this before to you, that this is how people were using computers to calculate x to the a. In other words, this is how computers were doing exponentiation. They were using logarithms. And you could see what was happening, because whenever it failed, when you had an invalid argument, it would send you back a logarithm error. And when I was your age, we were wondering, why are we getting a logarithm error? And it was because it was using this. This would be a language like Fortran. I presume other programming languages do this as well. This is an efficient and effective way to calculate powers. Okay. Now we'll talk a little bit about Taylor series. And remember that what's going to happen with a Taylor series is we're going to have a point of expansion. So we want to look at a function f of x. We want to look at a point at a, which we're going to expand around x minus a multiplied by the derivative with respect to x of a, and then x minus a squared over 2 factorial. Again, this is a Taylor series formulation. Second derivative and evaluated at a, x minus a cubed over 3 factorial. Third derivative evaluated a, and so on. This is a definition of a Taylor series. Now, clearly, you don't want to get too far away from x with a. So what would be a good value in your mind to use for a that would make life easy? 0. Okay, 0. So a lot of times you'll see, almost always, we're going to expand our Taylor series around 0. You don't have to. It can be anything. But you're going to see that we're going to try to expand it around 0. Okay, graphically, what we would look at is the first term. If we were looking at f of b, it would simply be equal to f of a, which is explaining it in this fashion. And then we add the next term, which is going to be this linear term. So f of b is equal to f of a plus b minus a, which is this distance, multiplied by the derivative. So it would be up here. The actual value for each case is here. So the first approximation is just to say that it's a step function, and the first value is equal to, or sorry, the second value is equal to the first value. The next approach is a linear extrapolation. The next approach is a quadratic extrapolation. And as you can see, as we keep going on and on with higher powers, we'll eventually make that connection. But again, a and b need to be kind of close to each other. And again, we're probably going to choose a to be 0 for most of our applications. Okay. So the Taylor series itself, how do we obtain it? We take the infinite series, and I apologize for the crappy handwriting, but n equals 0 to infinity, a to the n, x minus c to the n. We simply expand it out, and then we take its derivative, take the second derivative, take the third derivative, and by doing this, you can see, okay, a0 is here. It's simply equal to f of c. a1 is going to be equal to f of c prime, and so forth. You can see that by how these terms get carried out. Okay, so in our case, how we're going to evaluate this is if we say that x is equal to c, then the first term is just going to be evaluating that at c. So a0 is equal to c. The second term, a1, there is no a0. It's going to be equal to f prime evaluated at c. The second term is going to be 2 times a2 evaluated at the second derivative evaluated at c, and so on. So you can see the pattern forming. Of course, 2 factorial is 2. 3 factorial is going to be 3 times 2 times 1, which is implied here. So the last time, all of these other terms cancel out when you choose x to be equal to c. But here, it's the third derivative evaluated at C, and then 3 factorial multiplied by that. So all of these coefficients work out this way. The general formula is a to the n is equal to 1 over n factorial. The derivative, the nth derivative, pardon me, evaluated at C. So that's your Taylor series, very straightforward, and so on. Now, how are we going to apply this? Well, we're going to, and this is just a repeat of what we saw before, we're going to come over and we're going to apply it to the exponential. Now, what's the good news about the exponential? Let's pick on somebody we haven't picked on yet. Who wants to volunteer? Let's see. Where's Mr. Syed? Okay, you ready? This is the easiest thing you've ever done. All you just have to do is say the right answer. Okay, what's the derivative of an exponential? What's the derivative of a derivative of an exponential? What's the derivative of a derivative of a derivative of an exponential? Okay, do you see the pattern? They're all exponentials. And so when we evaluate them at 0, they're all 1. So all of these coefficients become 1. So the Taylor series becomes 1, duh. X minus 0 times 1. X minus 0 squared over 2 factorial times 1. X minus 0 over cubed, 3 factorial, and so on. So this is how we derive the Taylor series for the exponential. Now, how many of you think this is accurate enough for you to use? Nobody's raising their hand because you know this is really too simple. When you take your first reservoir simulation class, they're going to talk about estimating like formation volume factors for the constant compressibility liquid case, and you're going to use chord slopes. The reason you're going to do that is because of a relationship that's sort of like this, that you want to have a very simplified single term expansion for this. Comments? I started to say, what's the penalty for using this expression? Okay, no hobbly English, no problem. So back in 1955, Mr. Hastings and Ms. Hayward and Mr. Wong, they came up with a book, and this is in your reference section, on how to calculate functions. What operations do we have at our disposal? Add, subtract, multiply, divide, and logic. So here, the exponential e to the minus x is evaluated with a 1, 2, 3, 4, 5, 6 parameter equation. X varies from 0 to infinity, and it's a simple polynomial. Here are the coefficients, and over here they raised the whole thing to 4. Not sure why they did that, but they did. And supposedly this thing is accurate. It's single precision, which is just a few decimal places, but it should be accurate over the entire range from 0 to infinity. What should this thing do at x equals infinity, class? It should go to 0. Okay, what should it do at x equals 1? Or sorry, x equals 0. Okay, and so x equals 0, 0, 0, 0, 0, 0. All that's left is 1. Raised to the 4th power, it's still 1. So at least on that end, it sort of makes sense. I realized this a long time ago, 61 years ago. Would you have done this differently if you were writing the book? Any of you guys familiar with the Cold War, you know? Yeah, okay. So if there was a book by some guys at Princeton, there must be a book from some Russians, right? And that's also included in the reference. The Russians, I think, you know, they're actually a derivative of people from Louisiana, because they always have to do things the hard way. And they started with things like Taylor series, and then they did something that's not very effective for, and again, if you were educated in the Soviet system, my apologies, but they seem to like, near zero behavior and near infinity behavior. Well, what about in the middle? And so what they would usually do is come up with something with an equation for near zero and come up with a solution for near infinity, and then they'd somehow figure out some way to tie them together. Any you guys Boy Scouts or ladies Boy Scouts? No? Yeah, you were? Do you remember how to splice rope? You know, splicing rope like that? Not tying, splicing. Anybody can tie a knot. I'm talking about, merging them together. Yeah, does it get bigger at the splice? A little bit bigger? So if you have a function that's spliced together, the Rubin function, along with the David function, along with the Susie and Sam function, what's going to happen whenever you're walking along that rope? If you're going to bounce a little bit, okay? So when you take the derivative of that equation, what's going to happen at those splices? Boing, 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 boing. And when you look at some of the old work, especially things that utilize these equations, you'll see that they went nicely behaved, and then boing, 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 and then kind of like this. Also, what's the problem with rational polynomials like you see here? Ah, you went to French school. Yeah. What happens if we hit a root? That's worse than a boing, boing, boing. That's a kabloom, okay? So rational polynomials, we hope that the roots are on the outside of where we're looking. But if there happens to be one in the middle, just by accident, kaboom, it doesn't work either. So maybe some of the criticisms you could give the Hastings work is they mostly worked in rational polynomials. Why? Why did they work in rational polynomials? What were our operations? Okay. And what better than a polynomial over a polynomial? You guys ever thought about this? They have a lot more flexibility. Uh, you'll see later. You don't believe me now, but you will. Okay, and then here's our Russian friends, and their book came out, I want to say, in 1965, but that was when it came out in English. It probably was a little bit earlier than that. And you can see that they were working on more or less a Taylor series type expansion. Here's the expansion as a rational polynomial, and here's an expansion for something that looks, smells, and tastes like a Taylor series. It might be slightly optimized. The difference here is this is only valid for arguments of x less than 1. Of course, I understand this is e to the x and the other one's e to the minus x, but that's okay. We can simply work the algebra or the sign differential. So as an example, most of the things in the Russian book had some sort of an applicability range. Again, like I told you, they like things that work near zero. So let's do a Taylor series really quick for sine of x. Anybody want to volunteer for this? What's the derivative of sine? Cosine. What's the derivative of cosine? Minus sine. What's the derivative of minus sine? Minus cosine. What's the derivative of minus cosine? Sine. What's the derivative of sine? Oh, we got a pattern. So then when we evaluate them at x equals 0, we get 0, 1, 0, minus 1, 0, 1. Guess what the next one's going to be? 0, minus 1. So when we substitute these, we end up with a pattern. All the positive terms are killed, and we have an alternating sign, SIGN series. So our sign becomes only the odd powered terms remain. X to the 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial, dot, dot, dot. And here's our general formulation. Do you think this is going to work very well? What's your intuition tell you? Yeah? Okay, well, here's sine of pi over 2. They did that so they could map it onto minus 1 to plus 1. And you'll notice they used a polynomial. Does anybody know what this number is right here? Pi over 4? 2. Yeah, pi over the square root of 4. Thank you. Okay, so did you expect that? Because they've got pi over 2 here. This should have been a 1, right? That's what it said. That coefficient should have been a 1. So it's not a surprise that the first term is pi over 2. And you could probably go back and remap these coefficients onto here and be fairly close. Now they were using something called min-max optimization to fit this, and you can see these are the error curves down here. This is not sine exact. This is not the sine function. This is a difference between the calculated and the measured. So that worked out okay. And then let's see, did we do anything for the Russians? No, we didn't. That was the end of that discussion. So if you're looking at a computer program and you're going to calculate something, what's it going to end up being at the root? It's going to end up being addition, subtraction, multiplication, okay, division, and a logic. All right. You can build more complicated functions from this, but you notice that neither of these had anything more complicated than polynomials. Of course, this is e to the minus x. But then could you come back and do things with this function? Could you make other functions out of e to the minus x? I'm trying to build in your brain that you know there's an error curve to this e to the minus x. If you use it for something else, what's going to happen? There could be an error curve for it, and it could compound. Okay. So back during the 50s, 60s, and 70s, research institutes spent a fortune in time and effort trying to create machine precision relationships for something like e to the minus x or cosine. If you start looking at old, if you type Fortran code for cosine of x, some equation 3 pages long will come out. Okay, and that particular organization probably patented it or something like that. Do you have access to how Microsoft calculates e to the minus x? No. Do you have access to how it calculates cosine? Do you have access to how to calculate special functions? Do you have access to that in MATLAB? Do you have access to that in Mathematica? Now, like I said before, when Fortran was just coming out, you had to write a subroutine or a function call for this. So you'll look back at the literature. If you log on right now and say, show me a function, Fortran function for calculating cosine x or calculating something else, you'll see a piece of source code come up because that's what you had to do. Okay, I'm going to stop.